It's the end of the road for the old acids and bases. The last type of solution that we'll look at in Chapter 14 is a salt solution that ends up slightly acidic. A good example is this ammonium chloride. All ammonium compounds are highly soluble or aqueous, so we can dissociate this completely. In the solution, we would have ammonium ions, NH4. We would have chloride ions, and there's always water present. Water molecules, the major species in the solution. And so then when we're trying to decide if the solution is acidic or basic, we ask ourselves two questions. Number one, are there any particles here that could remove hydrogen from the solution? Any particles that could decrease the hydrogen concentration? And usually then I'm looking at a negative particle, something that might be attracted to a positive hydrogen ion. In this case, chlorine. But then we say, wait a second, hydrogen, chloride, HCl, that's strong acid. That stays dissociated. So hydrogen and chlorine would not form a compound that technically removes hydrogen from the solution. There would stay individual hydrogen and chlorine ions. HCl is a strong acid. Second question, are there any particles that could produce hydrogen, that could increase the hydrogen concentration? And then we look at the ammonium ion, NH4 plus 1. And we say, ooh, that ammonium ion, that is the conjugate acid of the weak base, ammonia, NH3. And if we remember anything about like weak acid, weak base solutions, remember this. The weak base, ammonia, NH3, picks up hydrogen from water, forming the ammonium ion. And the other particle left is hydroxide. Okay, so we had said that this ammonia acts like a base, and this ammonium is this conjugate acid. If we shift this in reverse, then the ammonium NH4 ion has to relieve his extra hydrogen. Well, if this is a weak base, we'll put this here, weak base, that means the equilibrium really lies in reverse. We really favor the reverse, making this ammonium ion relatively strong. Relatively strong. We had said the conjugate acid of a weak base is a pretty good acid. That ammonium ion really does have a tendency to lose his extra hydrogen, which then can react with hydroxide and shift this thing in reverse. So this ammonium ion does have some acidic properties to it. Now there's a couple ways that you might see this written then. You might see it kind of like what they have here, the ammonium ion just dissociating to form ammonia and hydrogen. Or often you'll see water in the expression. Because again, this is like a weak solution, you might see this written as NH4 plus 1 reacting with the water molecules that are also present in the solution. We do form the ammonia, NH3, but then the other particle might be written as H3O plus. Either way, I form two particles that both have some acid-base properties. We just mentioned that this guy, ammonia, is the sign of a weak base. But then I've got this hydronium ion. Or here they're just writing it as hydrogen. Yikes. That concerns me. That's going to be a significant source of hydrogen. I want to know how far forward does this go. How much hydrogen or hydronium is formed? The other particle, the ammonia, weak base, again, if it's a weak base, it really means that it stays neutral NH3 molecules. Does it have the ability to pick up extra hydrogen? Maybe, but it's very, very weak. So I'm concerned with the amount of hydrogen or hydronium in the solution. So let's look at an example. Let's find a good one here. How about a 0.1 molar ammonium chloride solution? Okay, so we just said that the major factors, the major species in the solution are the ammonium ion, the chlorine ion, and water. The chlorine is a spectator. We're going to completely ignore the chlorine. He cannot provide hydrogen. Obviously, he can't produce hydrogen. And he can't really remove hydrogen from the solution either, because hydrogen chloride, HCl, is a strong acid. It stays dissociated. So the chlorine is our spectator. We've got ammonium ions and water molecules. So we want to write an equation that shows this setup. And H4, the ammonium ions, are slightly acidic. They will be hydrogen donors, donating their hydrogen to the water molecules. We'll form NH3 ammonia and the H3O. And again, if you wanted to leave the water out, it would be fine. In this case, it really is fine. Often the hydrogen is transferred to the water because it's attracted to the negative oxygen end of the water molecule. But when we set up an ice table, we're not going to use the water anyway. So we could just even scratch that right now. It's a pure liquid. The concentration of ammonium ions will be this 0.1. And we do not have any product. So we're shifting forward by x minus x plus x and plus x. So at equilibrium, I'm looking at 0.1 minus x, x, and x. And again, aren't you feeling like pretty confident with these acid-base ice tables now? They're very similar. This one is just a little goofy because you might have to set this equation up yourself. So you really have to understand what's going on in the solution, which particle will affect the pH, which particle will have either a significant increase in the hydrogen concentration or decrease in the hydrogen concentration. Okay, so we kind of mentioned too that between these two products, the ammonia is a weak base, but this could either be written as hydronium or just hydrogen. That's the one I'm looking for. The sign of an acid, strong acid. So we need to solve for x, and like we expected, this should be an acidic solution, so x should be the amount of hydrogen formed in the solution. Only problem, we're given Kb. We're given Kb for the weak base ammonia, but we're using its conjugate acid. Piece of cake. Remember this guy? Ka times Kb, 1.8 times 10 to the negative fifth, equals Kw, 1.0 times 10 to the negative 14th. Totally in the packet. We had to use it when we were doing the other solutions too, the salt solutions that were slightly basic. Okay, so we have to do an extra step here. We have to calculate the Ka, since we are using the conjugate acid of ammonia. So I plug that in my calculator. Ka is relatively small, 5.56-ish times 10 to the negative 10th. And then we can set up our equilibrium expression, which I think most of us are getting good at these, right? X squared over 0.1 minus x. That K is crazy, crazy small. So we're going to 5% rule it, which just makes my math a lot quicker. So we're going to cross multiply. 5.56 times 10 to the negative 10th times 0.1. That's not bad. And then we're going to square root. So I get x as about 7.46 times 10 to the negative 6. Excellent. And did I check the 5% rule? You bet I did. I qualitatively checked the 5% rule to make sure that x was small. Since that K value was crazy small, yes, we're going forward, but probably not by much. So x is going to be tiny. 10 to the negative 6th, that's small enough for me. If I were to take 0.1 and compare it to 0.1 minus x, those values will definitely differ by less than 5%. And again, the 5% rule always works. It is a sure thing because you do not need the quadratic on the AP test. Okay, so I have x, and of these two products, the one that I'm most concerned with is the sky. And actually, this one's a little easier now because X is the hydrogen concentration. So right away, we can just go pH equals opposite log of the 7.46 times 10 to the negative 6 molar. Hydrogen, hydronium, either is fine. All right, so we plug this in. And let's say about 5.1, 5.13, somewhere in there. And that's it, we're done. We've got the pH of this weak acid solution. Slightly acidic, which is exactly what I expected. Not bad, right? The worst part is really just setting up the original equation. Look at the two ions, ignore the spectator, and then you'll set up an equation with your particle that's slightly acidic, donating a hydrogen to water. You'll set up your ice table then to figure out the concentration of hydrogen or hydronium. The only other step in here is that we have to calculate the Ka. We're probably given Kb for the original weak base. Okay, so here we just quantitatively solve for pH. But you could also kind of do this qualitatively by inspection. This would be a good example for maybe a multiple choice question. They're going to give me some salts where both ions can either increase the concentration of hydrogen or decrease the concentration of hydrogen. And so we have to decide, is the overall salt going to be more acidic or more basic? Warning, they will not ask you to calculate the pH of these kinds of solutions. I mean, we can. It just ends up being kind of a pain. Sometimes you need more than one ice table. We have to consider the Ka values. You will never need to calculate the pH of these types of solutions. But we can do this. We can at least predict if the final solution should be more acidic, more basic, maybe it's neutral, by looking at their K values. So for example, what if I have a solution of ammonium acetate? And they give me the K values for the original acid and base. Okay, so ammonium has a K value of about 5.6 times 10 to the negative 10th, which is pretty darn close to what we just calculated, right? I think we used about 5.6-ish, 5.56 times 10 to the negative 10th. The Kb value for the acetate ion is about exactly the same. So you've got the ammonium ion, which is slightly acidic. It can release its extra hydrogen. You've got the acetate ion that can pick it up. But if their K values are essentially the same, this final product ends up being neutral. This would really just be a neutral solution. Both particles have the ability to affect the hydrogen concentration, but they have the exact same K value. Neutral. How about some ammonium cyanide? That sounds delicious, right? Ammonium's K value is 5.6 times 10 to the negative 10th. But the Kb for cyanide is greater, 1.6 times 10 to the negative 5th. So we're asking ourselves, who's going to have a more substantial impact on the hydrogen concentration? That cyanide ion is a stronger base. This final solution should be slightly basic. And the last one. Some aluminum sulfate. This is kind of an interesting example. Aluminum has a K value. It has the ability to react with water in the solution. And we end up with a K value of about 1.4 times 10 to the negative 5th. Sulfate is the conjugate base of sulfuric acid. But remember we said that the second dissociation, where you finally form the sulfate ion, is a weak dissociation. It's got a pretty small K value, doesn't it? If I compare these two, Ka for the aluminum is greater. This should be slightly acidic. And they're going to give you these numbers. You don't have to come up with them off the top of your head. We just have to do a little comparison. And it really makes sense. If both particles can affect the hydrogen concentration, we're looking for the one with the higher K value. That'll have a more significant effect on the hydrogen concentration. Good example of something that they could give us maybe multiple choice style. Otherwise, again, sadly, here's the end of it. Another chapter in the books. Only 15, 16, 17, 3 more to go.